exposed the singular value decomposition sum. I think it's worth creating 4 minutes of your life. Oh, isn't this sound?
It had to be you. You detranspose V. I looked all around and finally found the SVD. Singular vectors in V and U, orthonormal to singular values in D, positively made just for me and you, dimension 16 might never be seen, but to decompose, everyone knows there's a matrix routine. Thanks to all this you can do, find a matrix of rank 2. It had to be you, D transpose V, the SVD. It had to be you, D transpose V, the wonderful SVD.
The singular value decomposition, or SVD, is one of the most useful results in matrix algebra, with a vast range of applications in applied statistics, especially useful in dimension reduction. Any rectangular matrix P can be decomposed as the product of 3 matrices of simple structure, U, D, transpose of V, where U and V are matrices of orthonormal singular vectors, and D is a diagonal matrix of positive singular values in the ascending order. Suppose that a matrix P has the following SVD. Then a low rank, for example rank 2, least squares matrix approximation is easily obtained from the first 2 singular vectors of U and V and the 2 corresponding singular values. This result allows data matrices of high dimensionality to be approximated optimally by one of rank 2, so that the data can be visualized in a 2-dimensional space for ease of interpretation. As shown by this map of countries, in terms of their attitudes about whether mothers should work outside the home or not.
Yeah, this is actually kind of interesting. So, right, they have this. Each of the countries has 16 parameters, right? And so the data is 16 dimensional, right? So what they do is they use the singular value decomposition, right? They use the singular value decomposition and then create a rank 2 matrix that that basically gives a pair of coordinates. Right? The coefficients for the linear combination, right? The coefficients for the linear combination. So each country is associated with those 2 coordinates, and so you can use those coordinates on this map here, right? And so that allows you to get a projection of your 16-dimensional data on a two-dimensional map. And then from there, so here you notice that they've sort of said that to the left means liberal attitudes, whoops, and to the right means conservative attitudes. Upwards is polarized attitudes, and downwards is compromising attitudes, right? That's actually, that actually needs to be figured out, right? So once you have the projection, it's up to your sort of own human interpretation to understand what these axes actually mean, right? That's not given to you, right? Just the SVD or so-called principal component analysis, which is the same thing. Gives you the projection, but you don't know exactly what these axes mean, and that is, so you have to figure that out. You give me a second. I actually have something from the data science class. Let's see, where's that? Faster one. So give me just 1 minute. So I have something from the data science class where we used a pre-created package to do something like SVD for handwriting data. So just a minute, will not take more than 1 minute. So this is human handwriting, and they've taken it and scaled everything so that they all lie in squares, 8 by 8 squares. Okay, so this is, each of these small pictures is 64 pixels, right? And each pixel, has a numeric value associated with it, right? The darkness, right? So that is, each of these pictures, they embed in a 64-dimensional space, right? Embedded in a 64-dimensional space. And then, what you're hoping is that, within that 64-dimensional space, all the zeros lie in one region, right? All the ones lie in another region. That's almost guaranteed, that ought to be true. One way of seeing it is to do a dimension reduction. The thing that I just showed you is called dimension reduction, right? You've got your 16-dimensional data, you project it onto 2-dimensional data, so it's easy to see. Here's another version of dimension reduction, but it's not. It's related to SVD, but not exactly the same. And this one, are there any Pomona students here? No. Okay. This one is actually created by a professor at Pomona some years ago. Okay. So what this is a 2-dimensional projection of the 64-dimensional data. And as you see, like all the 4s are pretty close to each other, right? The ones are close to each other, the 2s are close to each other, et cetera, right? You see that 1s and 4s, some of the 4s look like 1s, which kind of makes sense, right? Right. Some of the 7s and 1s are close together. Again, makes sense. They do look like each other. Right. 5s and 1s. Yeah. So nines and threes, et cetera, et cetera. So this is another one taken from a different angle, basically. Another projection. You see that the sixes, maybe the ones and the eights looks. I don't know. Anyway, anyway, this is another example of dimension reduction, but a more modern version. The PCA or the SVD is restricted. Is a little bit restrictive because it's based on linear projection. So, so like it looks, you've got your data, and then it looks for a plane that approximates that data, right? So your data is sitting in some high dimensional space, and you look for some plane that approximates that data. But suppose your data, is not planar, right? Suppose your data actually lies on some sort of curve, lies on some sort of like roll, some sort of roll, right? In that case, your linear approximation is not gonna do that well. And so this method of isomap basically tries to unroll it and then make a flat surface out of it and then do the projection. By coincidence, on Facebook, a memory showed up from 13 years ago, in which exactly in a linear algebra class, somebody asked me, will you sing the SVD song for us? And I said, no. What am I, a dancing bear? But I guess I sang a little bit of it last time, so maybe I turned it into a dancing bear. Okay. Okay, so let's go on. We're going to finish up the SVD. So before we get there, I have to introduce, so let me just show you something. Don't worry too much about this, okay? I'm just going to show it to you. So this was something that I actually skipped over. I think this is from chapter 1, maybe like in a section that I just didn't go over because this doesn't really come into play until right now. Right? I wasn't really sure if we would make it here. So it's something called the outer product expansion. Okay. So you have two vectors. One is n by 1. The other, well, they're both n by 1 vectors. Right, so they've got n rows, right? N rows and 1 column. Right. Okay, so if we take x transpose y, right, then that's going to look like this, right? And that's going to be a 1 by 1, the dot product, the inner product. Right. So you get this inner product right here. Okay. There's something called the outer product, where instead of taking x transpose y, you take xy transpose. Okay. You take xy transpose, right? So this will be y1 through yn, right? This is an n by 1. This is a 1 by n. Right? And so, what do you get? Well, you get x1, y1, right? x1, y2, x1, yn, x2, y1, x2, y2, x2, yn, xn, y1, xn, y2, xn, yn. in other words, you get y1 times times x, then y2 times x, y2 x, yn x. Okay, and that's called the so the outer product. The outer product is defined as x y prime, x y transpose. Okay. Okay, and now I'm just going to put a fact that if you have a matrix, an m by n matrix, and a k by n matrix, then when you take the product x against y transpose, that is actually x. So as usual, we'll denote the columns of x are xi, the columns of y are yi. Then this actually turns into the outer product of the outer products of the corresponding columns. Okay. So it's a sort of like a sum of outer products. The book abbreviates it as x1, xn, y1 transpose, y2 transpose, y1 transpose. Actually, that makes sense, right? Because actually, let me write it the opposite way. So this thing, x is of course, x1, x2, xn. Y transpose is y1 transpose, y2 transpose, yn transpose. Okay, and that turns into this sum of outer products. Okay, that is the when you multiply these two matrices together, it's basically it basically works like a dot product. Okay. This probably is not 100% clear to you, but just accept it for now. Okay. You can go back and read it if you want. Okay. So the point is that when you have a matrix times the transpose of a matrix, then that's expressible as some sort of inner product, which gives you these sum of outer products. So this is sort of like outer product composition of a matrix product, if you want to give it a name. Okay, so now let's go back to the singular big. So now let's return to the singular value decomposition. So A is u sigma vt. Right, which we can think of as u sigma vt. Right? In other words, a matrix times the transpose of some other matrix. Okay. So what's u sigma? Right? U sigma is remember we've got the ui's, and then we have this diagonal matrix with the singular values down the diagonal. Right. Well, when you multiply that out, that turns into sigma 1 u1, sigma 2 u2, sigma n un. Right. So what is this? It's this, right? Is it okay? Okay. So now let me just throw on Vt, right? So that is going to be V1 transpose through Vn transpose. Right. V1 transpose through Vn transpose. And what you see is that that the singular value decomposition can be recognized as a sum of outer products. Yeah. I'm sorry, this should not be called a decomposition, but an expansion. Okay, so the S singular value decomposition has an outer product expansion. Okay. Namely, it's going to be sigma 1 u1 v1 transpose plus sigma 2 u2 v2 transpose plus sigma n un vn transpose. Okay. Okay. Is this all right so far? Any questions so far? All we've done is just use the outer value expansion over here, and then applied it to the singular value decomposition. Okay. So now observe. Observe, if we sum, so if for some k smaller than the rank of A, right, we sum only the first k terms. if we sum only the first k terms, the result is equivalent to so the result would be sigma 1 u1 v1 t up to sigma k uk vkt. Well, that is the same thing as if we just if we chopped off the sigma at the kth row. Okay. The punchline is this. This is a rank K matrix. This whole product here is a rank K matrix. And it turns out the best rank K approximation of A in some sense. Okay, so this should all be sort of like, okay, he's telling us this, I kind of believe it, I'm not sure what's going on at this point. Okay, that's where you should be. If that's where you are, that's okay. Okay, yes, Izzy?
Is it like quote unquote the best because it's the first K terms, which are like the K biggest terms, and everything less than K is going to be like smaller, so quote unquote more insignificant in a sense?
Yes, exactly. Yes. Yes, that's exactly how it happens. So basically, we're going to see that there's a distance. There's a distance between. There's a way of defining distance between matrices, and the distance. The distance between A and this matrix will turn out to be the smallest distance possible.
Gotcha.
Yeah. Okay. So this is just to give you this was the thing in the song, right? When they truncated it, what they did was they truncated it to the first two singular values, and they ended up with a rank 2 matrix, and that gave them their projection. Okay. So what we're saying here is that you can do that for any k. You can, and that will give you, in some sense, the best approximation. Okay. So yeah. So like I said, all of this should have been sort of like, I'm not sure what's going on. Let's put some ground beneath your feet. Okay. So okay. So Frobenius norm. Okay, so we probably didn't, I'm pretty sure we didn't use this term, but if you have a matrix, some n by n matrix, so let this be an n by n matrix, we define the Frobenius norm of A as kind of a magnitude, and it's just going to be, like your normal, vector norm. You take every single entry, you square it, you sum them all, and you take the square root of that, right? It's as if the matrix were one long vector. Okay, so nothing surprising. if we write A as, if we write A as a column vectors A1, A2, AN, and rows and columns, yeah, AN, then, so remark, notice that the Frobenius norm can also be thought of as taking the squares of the norms of the columns squares of the norms of the columns, everything to the 1/2, right? So J from 1 end. Is that clear? Is that clear? Right, because the norm of the column, right? The norm of the columns, right? I have some column, 1j, a 2j, a mj, right? The norm of the column is just, you know, it's just the sum of the squares, square rooted, right? So if I square that, right? If I square that, then I get the sums of the squares. So this is just the sums of all the squares, right? Right, the sums of the squares in each column. Well, that's just the sum of all the squares. Is everybody okay? You all seem a little funny today. Maybe I shouldn't have played the song at the beginning. That threw everybody off, including myself. Yeah, I don't think I'm going to play the song again. Yeah, kind of too slinky a voice for a math class. Yeah. Okay. Is this all right? Is this all right? Okay. Okay. So right, the sums of the squares of the norms of the columns. Blah, blah, blah. Okay. Okay. So Frobenius norm, you know, just pretending that your vector, I'm sorry, that your matrix is a long vector. Okay. So lemma. Let A be an n by n matrix, and Q be an n by n orthogonal matrix. Then the Frobenius norm of QA. So I take the matrix A and I hit it with an orthogonal matrix. Okay, I hit it with an orthogonal matrix on the left. What do you think happens to the Frobenius norm? Can anyone guess what happens to the Frobenius norm? Izzy?
I'll take a wild guess and say nothing.
Nothing. That is the answer. Nothing happens. Why? Well, just think. QA, that's Q times the matrix of columns A1 through AN. Right? Well, when you left multiply by the matrix, it occurs column-wise, right? So this would be QA1, QA2, QAN. Right? But remember, the orthogonal matrix, so nothing's going to happen, right? It's like guessing that the answer on a multiple choice question was 1. Okay. Right. So what's QA? QA is just, you know, it's just A with Q applied to each of the columns, right? But remember that Q orthogonal means that that the size of QA is the same thing as the size of Q. When you apply orthogonal matrix to a vector, it doesn't change the size of the vector, right? right? Do you remember? This is because right, the size of QA squared is the inner product of QA against QA, right? But then when we pull this to the other side, we get the transpose, right? This is going to be AI transpose Q AI, right? But this is 1, right? Because it's orthonormal, right? And so we just get AI squared. Right. So, and remember, so the size of QA, which is the sum of the size of the columns squared, quantity to the 1/2, is the same thing as the sums of the sizes of the AI squared to the 1/2, right? But that's the size of A. By the remark. Are you okay? Everybody okay? Okay. Right. Okay. Remark. It's easy to show similarly that that right multiplication by an orthogonal matrix also doesn't change the Frobenius norm. Just basically transpose everything, and then you'll get that result. Okay, so corollary. If A equals U sigma Bt is a singular value decomposition of A, then the Frobenius norm of F, the Frobenius norm of A is going to be well, think. This thing on the left is orthogonal. It's not going to change the Frobenius norm, right? This thing on the right is also orthogonal. Not going to change the Frobenius norm, right? So the Frobenius norm of A is actually the same thing as the Frobenius norm of sigma. Sigma was a diagonal matrix, right? Sigma was a diagonal matrix with like little sigmas down the diagonal, right? Well, what's the Frobenius norm of that? That's just going to be the it's just going to be these guys. Right? That's Frobenius norm of sigma. Okay, so Okay, so that's sort of the background, the background information that allows us to state the problem. The problem is, given an n by n matrix with R being the rank of A, fix some k smaller than R, and let M be all n by n matrices of rank k or less. Okay. So the question is, can we find a matrix X in those lower ranked matrices such that the distance between A and X is minimized and is minimal? Okay, and the answer is, of course, that yes, we can, and in fact, it is that thing that we said earlier, sigma 1 v1 transpose plus sigma k vk uk. I.e., it's u times sigma 1 to sigma k. It's the you get it by doing the singular value decomposition and then truncating the singular values at the kth one. The distance between these two let's call this thing x, or let me call this s sub k. The distance between A and S, the Frobenius distance between A and S of k turns out to be sigma k plus 1 squared plus sigma n squared, everything to the middle. Okay, so yeah. Okay, I think maybe I'll stop there, because I said that we would take a class picture today. Is that okay? Now that I've depressed you, all of you.